Hello class. Today we're going to be taking a look at rational functions. We've been doing a lot of other things, and I think we've laid the groundwork with inverse functions to now talk about rational functions. I don't believe you're going to find this particularly hard. Hopefully it's quite easy, considering you have done linear equations and you know how to graph those, and you've talked about inverse functions now, you've talked about square root functions, even exponential functions, so I think this one should be pretty straightforward. Rational functions. So let's switch on over to our whiteboard and get started. Okay, so a rational function has an important aspect that we need to look at. We need to be extremely careful that we do not divide by zero. When we were dealing with inverse variation, actually we're dealing with rational functions. So if we have an equation that looks like this, y equals some constant k divided by x, this is the way we express an inverse variation. But if you'll recall, we must not have 0 for k. K cannot be 0 because then it would be 0 divided by something and you would have 0, and you really wouldn't have a function, would you? You just have y equals 0. Well, so let's not let k be equal to 0. Secondly, let's not let x be equal to 0, because if x was equal to 0, then we would have an undefined situation, x not equal to 0. So y equals k divided by x, where x is not equal to 0. Now let's take a specific example and just consider it for a moment. What if we have y equals 5 divided by x? Okay. Then we would say that the excluded value, the value for x that we cannot use, is what? The value that we cannot use is 0. 0 cannot be in this domain of this function, and the reason is it creates an undefined situation, an undefined quotient that becomes infinitely large if we divide by 0. Now, I just want to review you briefly on the graph of this. Y equals 5 over x. Let's jump over here to our calculator and take a look at it. And I'd like to point out some things. Yeah, let's go ahead. So here we have y equals 5 over x. I want you to look. I've already put the equation in here. Y equals 5 divided by x. It's the blue line. Okay, y equals 5 divided by x is the blue line. So notice that it is approaching the red line. What is the red line? X equals 0. Right here it is. Let me turn it off so you can see it. This is the red line, the equation x equals 0. It is the excluded value, the value that you cannot put in the denominator. You cannot put 0 in the denominator. So notice that the blue line is approaching the red line. The red line has a name. It's called a vertical asymptote. Okay, a vertical asymptote. And the blue line is approaching that because when x is approaching 0, the function becomes infinitely large, going up. Let me zoom out here a little bit so you can see. That blue line approaches the red line, but theoretically it never touches the red line. Okay, it never touches the red line. Secondly, if you come to 0 from the left side, in other words, if x is approaching 0 but as a negative number, it will become infinitely large in the negative direction. And of course, if x approaches, if x becomes infinitely large, either positive or negative, the graph will also approach y equals 0, because if you divide by a very, very large number, okay, very, very large number, then the quotient will approach 0. So we have actually both a horizontal and a vertical asymptote. An asymptote is simply a line which the graph approaches but does not touch. Okay, a line which the graph approaches but does not touch. Now you may wonder, does it really not touch? Well, for practical purposes, you could say it touches, but in theory, it never touches. If you go out here farther and farther and farther, you'll see it's getting closer. See how this line is getting closer and closer and closer? 0 to y equals 0. However, there's still a little gap. And in theory, you can go as far as you would like, but there's still a teeny weeny little space between those two lines. Now, I realize maybe that seems odd to you, but in theory, okay, we're talking about in theory here, it's not yet touching because, you know, how small can you make a number? This is the question. How small can you make a number? Infinitely small. You can just add another 0, 0.000000001. That's a pretty small number, but you can still add another 0, can't you? So what's going to stop you from adding another 0? The number can become smaller and smaller and smaller and smaller, which means that we can approach but not touch. We can approach but not touch, okay? So this is an interesting concept that I hope can make sense to you. We're also approaching this line. We're also approaching the line y equals 0, okay? We're approaching this one as well. And let's see if we can get a different color on here. What is this thing doing to me? So notice here that we have a second asymptote, the horizontal asymptote, y equals 0. This guy right here. See it? Here's our vertical asymptote, x equals 0. That's the one that that's the value of x that creates 0 in the denominator, okay? And then here, of course, is our graph of our inverse relationship, okay? 5 over x, okay? So some terminology, vertical asymptote, horizontal asymptote. And an asymptote is simply a line which the graph approaches, a line which the graph approaches. So again, in this equation, x cannot be equal to 0 because the function becomes undefined when x equals 0. And x equals 0 is referred to as a vertical asymptote. Let's write that down here. It's a vertical asymptote. There. Vertical asymptote. This is created when a line is approaching the other line. Or this is a situation where the line approaches another line, the graph approaches another line, and that other line is called the asymptote. So our vertical asymptote for this example is x equals 0. That particular line is our vertical asymptote. I'll go back here and see it again. This is our vertical asymptote right here, okay? Because the graph, the blue line graph is approaching that particular value. And again, the graph also is approaching the x-axis in this particular situation, which is y equals 0. You can see this one. So we also have a horizontal asymptote. And we should probably write that one down. Okay, horizontal asymptote. In this case, y equals 0. Okay, so we have two asymptotes, horizontal and vertical. So let's take a look at an example that will help us to see this. So our first example is y equals 3 over x subtract 1. Now 3 over x is going to look pretty much like the last illustration I had, which was 5 over x. The only thing is the graph will be a little closer to the origin. It will pull in a little tighter to the origin, and it will be translated. Where will it be translated? I hope you're saying, well, subtract 1, that's going to translate it 1 unit downward. And if you're thinking like that, you're exactly correct. So now, which is the excluded value, the value that we cannot use for x? Which is the excluded value from the domain? Which value can we not use for x? And I hope you're saying, well, that's simple. We've done that before. X cannot be equal to the thing that makes the denominator 0. And in this case rather, x cannot be equal to 0, because if you made x 0, then the denominator is 0. X cannot be equal to 0. Let's take a look at our graphing calculator and just see how this thing looks. Let's graph it and take a quick glance to see how it looks. Okay, here we are back to our graphing calculator. Let's take a look at this example. Y equals 3 over x subtract 1. Now again, x cannot be equal to 0 because when it is, we have an undefined function here, and that would be, x equal to 0 would be our vertical asymptote. Let's turn it on right here. Okay, and let's make it so we can see it. Let's go to our settings here, and let's make this guy a dotted line. It's a little easier to visualize that way. And let's go ahead while we're at it and make this guy right here a dotted line as well. All right, here we go. So once again, this is our graph right here. This is our graph, the red line. Again, it looks like our other graphs, except it has been translated 1 unit downward. That 1 unit has effectively moved the asymptote down to where the green line is. Notice the green line, the green dashed line. If I click on it, it'll get bold. So the red line now, the red graph, is approaching to this horizontal asymptote of y equal to -1. And our vertical asymptote is the same as it was in our first example that I was showing you. It's still x equals 0, this one. We haven't done anything different to the denominator to require us to make any alterations. It's still just x equals 0. Okay, so again, x equals 0 is the vertical asymptote. Y equals -1 is the horizontal asymptote. Okay, so back to our whiteboard. So we can say that the vertical asymptote is the line x equals 0. And the horizontal, I'm going to start abbreviating to speed this up. The asymptote for the horizontal one is y equals -1. Y equals -1. Now notice that this guy right here defines our vertical asymptote, and this guy right here defines our horizontal asymptote. Okay? Notice that pattern and how it works. In example number 2, we're going to take the same expression, y equals 3 over x, except that we're going to subtract 1 from x in the denominator. Y equals 3 over x minus 1. Now remember, division by 0 is not allowed. We can't divide by 0. So how would you get 0 in the denominator? Well, if you wanted 0 in the denominator, Actually, we don't want 0 in the denominator, but if you were to have a 0 in the denominator, which value of x would give you 0? That would be the value, like so, sorry. That would be the value, this, x minus 1 equals 0. How could this be true? What value of x would give 0 down here in the denominator? Well, take this guy to the other side, and you would see that x is equal to 1. X equal 1 would give 0 in the denominator. Therefore, it is the excluded value. We would say in this case that x cannot equal to 1. X cannot equal to 1, because if x equals 1, then the quotient becomes infinite and we have an undefined situation. So again, x cannot be equal to 1. So when you're trying to find the excluded value from the domain, the excluded value of x, the value that x cannot equal, when you're trying to find that, then you look for the value of x that creates 0 in the denominator. And that's the value you cannot have. So x cannot be equal to 1. Now, what do you suppose happens when x equals 1? It blows up. We have this graph shooting off infinitely high or infinitely low, creating an undefined situation. So as we had above, up here, notice the value of x that created 0 in the denominator was x equals 0. And so that is our vertical asymptote, x equals 0. Down here, it's not 0 that creates an undefined situation, it's 1. So the vertical asymptote forgot my P, is going to be x equals 1. Okay, that's our vertical asymptote. Okay, x equals 1. And the horizontal asymptote is just same as it always was. It's going to be y equal to 0. Okay, to save time, I'm just going to abbreviate, okay? Horizontal asymptote is y equals 0. Let's jump over to our Desmos graphing calculator and have a look at this and see if it makes sense. So I've entered the function here, y equals 3 over x minus 1. Can you see from the graph the line that the red graph is approaching? Can you see it? What line is the red graph approaching vertically? Okay, what is our vertical asymptote? I've already told you, but take a look at this. Can you see that it is approaching 1? Let's go ahead and throw that in here. So here we have y equals 3 over x minus 1. Take a look at what has happened now to our asymptotes. Particularly, I want you to see the x equals 1 right here, x equals 1. Look at this function right here, x equals 1, this straight line. This is the line that the graph is approaching. And if you look back at the denominator, you'll see that x equal 1 is the excluded value. If you have x equal to 1, the denominator becomes 0. So x equals 1 is the asymptote, okay? The asymptote, the vertical asymptote to be precise, is that value of x which creates 0 in the denominator. X equals 1 will create 0 in the denominator. Therefore, it is excluded, and it is also our vertical asymptote. Notice that if you let x become really, really big, moving down here, if you can follow my cursor, if you go this way with the x-axis, x is becoming larger and larger and larger. Follow my cursor over here now on the left. See, if this x value becomes super large, the quotient will become super, super small and approach to 0. So this one right here is our horizontal asymptote, and it's y equal to 0. So again, if x becomes super large, either positive in positive direction, over here on my right now, if we go this direction, x is becoming really big, the fraction is becoming really, really small, approaching zero. Or if we go in the negative direction, it's also becoming super, super small and approaching zero. So it doesn't matter if you go right or if you go left, you approach zero. The only difference is that if you go to the right, you approach zero from above. If you go to the left, you approach zero from below. Okay, turning this guy back off so you can see that a little more clearly, zooming in so we can get a better view. Notice here, yeah, zooming out just a bit. Okay, here. So notice if we go to the right, you're approaching zero coming down from above. If you go to the left, you're approaching zero coming up from below the horizontal asymptote. Okay, I hope that makes it clear what we're dealing with. Back to this again. Notice that the vertical asymptote is x equal 1. The horizontal asymptote is y equals 0.
Okay, class, now we're ready to go on to example number 3. Sorry, I had a little pause there. I had to go take care of some business and attend a meeting. In any event, example number 3. Let's jump back to our whiteboard and take a look at this. Okay, so here what we have is y equals 2 over x plus 1 minus 5. Y equals 2 over x plus 1 minus 5. Now, based on what we've already learned, we know that the denominator of this expression cannot be 0. So look at the denominator, 2 over a denominator of x plus 1, x plus 1. What value of x would make the denominator to be 0? That's the question you have to answer. What value of x would make the denominator 0? I think, and I hope, that you can easily see that if x was negative 1, then you would have negative 1 plus 1 being 0. So the first thing we'd want to identify is that x plus 1 cannot be equal to 0. And that would mean that x cannot be equal to negative 1. Okay? What would negative 1 be? In terms of these asymptotes that we've been talking about, what would negative 1 be? That would be the value of x for which the expression blows up. It would be the value of x for which the expression becomes infinitely large, either in the positive or the negative direction. So I'm going to suggest to you that this value of x right here that creates a denominator of 0 is, in fact, our vertical asymptote. Okay? X equals negative 1 is our vertical asymptote. So sorry, picking up the wrong pen here. And it doesn't want to undo. Hang on a second. X equals negative 1 is our vertical asymptote. How about the horizontal asymptote? Now, on the first inverse variation problems we did, we had something like y equals k over x, where k is some constant, and x cannot be 0. If x was 0, then y becomes undefined. And that value, or those asymptotes, were in fact the x and y axes. They were the axes. But now we are subtracting 5 from this expression. That means the whole works is going to be translated down 5 units. In addition, the negative 1 is going to push us to the left by 1 unit. So if you think about the denominator, the value of x for which we have an infinitely large quotient, an infinitely large value of y, that value of x is -1, which means we've been pushed to the left by 1 unit. If it wasn't for the +1 right here, if it wasn't for this guy, then the vertical asymptote would be at x equal to 0, okay? But now it's at x equal to -1, okay? So I'm going to go ahead and write this on here. The horizontal asymptote then would be x equal -5, okay? Sorry, not x, excuse me. It's y equals -5. So let's jump now to the Desmos graphing calculator. Take a look at this expression and see if it makes sense. Let's try to understand this. Again, we're looking for the asymptotes of 2 over x plus 1 minus 5. Here we go. Here's our expression, 2 over x plus 1 minus 5. You see it up here in the left-hand corner, our first function that's been placed there. I need to find my cursor. Oh, here we go. Okay, so here's our first one. Okay, let's turn off these guys right now. So here's our function, y equals 2 over x plus 1 minus 5. Notice that it's shifted left by 1 unit. Where's 1 unit? Well, 1 unit would be right here. Okay, you see where my cursor is. This is 5, 4, 3, 2, 1, right here. So this was originally, before we did the x plus 1, when it was just x, it would have been this vertical axis right here, the y-axis. However, by adding 1, we pushed it to the left by 1 unit. Okay, and then, as I think you can easily see, we've been translated downward 5 units. 1, 2, 3, 4, 5. So this right here is the horizontal asymptote y equals -5. So let's turn these on one at a time. First of all, let's do our vertical. X equals -1. Right there it is. Let's highlight that a little more. You see it? This is our vertical asymptote, which has been shifted to the left by 1 unit because we went x plus 1. And x equal to -1 is, in fact, the value of x that creates 0 in the denominator. So that's our asymptote, x equals -1. And then we've been translated downward, which is our second graph right here. We've been translated downward 5 units to get our horizontal asymptote right there. So I hope these 3 examples help you to understand, number 1, what is an asymptote? Can you answer that question? What is an asymptote? It is a line to which the graph approaches but does not touch. Now again, you may say, well, it looks to me like it touches. Well, looks are deceiving, okay? In math, we can go to infinity. So we can be infinitely small or infinitely large. The reality is that these asymptotes are never touched, even though we keep approaching closer and closer and closer to them as the value of x extends in either direction, either positive or negative, okay? Then secondly, the y-asymptote, again, is that value to which the function or the graph of the function approaches in a horizontal position. So that's the one we're on right here. This right here is our horizontal asymptote. Again, it never touches. And this is our vertical asymptote. Again, it never touches, though it gets closer and closer. Okay, remember, division by 0 is not allowed. When you divide by 0, what happens? Well, you're looking at what happens right here. The graph shoots way up high or way down low. And as you go to greater and greater values of x, then your denominator becomes infinitely large. So what happens to 2 over x plus 1? Let me go back to the other whiteboard. What happens to this quantity right here as x becomes bigger and bigger and bigger and bigger, either positive or negative, doesn't really matter either way. What if I said x was equal to 1,000,000? Then I add 1 to 1,000,000. Do you think the 1 has much of an impact on the million? It's 1,000,001. So what's 2 divided by 1,000,001 as compared to 2 divided by 1,000,000? Essentially, they're the same thing, aren't they? So as we get very, very large values of x, either positive or negative, this expression right here, this whole expression goes to 0. Okay, it gets smaller and smaller and smaller and smaller. Okay, and then of course we're subtracting 5 right over here. We're subtracting 5, which translates it down. But if we weren't subtracting 5, it would just be y equals something very, very close to 0 as x becomes very, very large. And that's why on the graph here, you see that if we go far to the right, follow my cursor, if we go far to the right with x, we're coming down to this line, -5. If we go far to the left, we're coming up to this line, -5. And in fact, if I take away the subtract 5, you'll see then we're back up here. We're back up to the x-axis, okay? We're back up to y equals 0. So this expression will be y equals 0 in the event that we have very large values of x, either positive or negative, but very large values of x, y becomes 0, very close to 0. It approaches 0. So the asymptote would be y equals 0, like this right here, okay? It would be y equals 0, all right? So hopefully that makes this section 11-2 clear to you. I'm not going to emphasize it a whole lot. So we're not going to do many exercises on this. I'm going to move on to 11-3, which I feel is probably a little more important for you right now at this point. You'll cover things like this in Algebra 2 and in great depth as compared to what we're doing right here. So I think this is just an intro. Remember, what's the key to learning well, to remembering? One of the best ways to remember things is to see them many, many times. And it doesn't matter even if they're short exposures, you will still remember better if you've seen them. So short, repetitive exposures helps you a lot. So you've seen this stuff here. You've seen what is the concept of an asymptote. That'll help you later on. So I'm going to switch back over here and tell you all goodbye for this video right here. So I hope you've enjoyed it. Yeah, math, you can actually enjoy math. What? You're surprised? You shouldn't be. Math can be a lot of fun. So work on your little exercise. It's going to be a really short one. So rejoice in that. But I will be putting up 11-3 shortly to push you forward with that. So remember that next week will be the wrap-up of school. I didn't say that right. It's the wrap-up of instruction, and then we have exams. So exams will be coming starting on the 11th, 12th, and then the following week, 15 through 19, depending on what class you're in. Some classes may end by the 17th, so your exam might be over by the 17th. Others may stretch on to the 19th. But in any event, we've spread them out over quite a few days, so you shouldn't have many exams on any given day. Probably just one, actually. Probably only have one exam on any given day. So that's good news to you. Well, blessings to you. Enjoy your homework, and I will get busy on the next video.